Yes, students, good morning, all of you. Myself, I'm Vijay Kumar. I finished my PhD and having a GATE rank of All India 347. And I have a GATE experience of 10 years. I'm going to teach you today this session and production smart methods for solving the questions. Okay, as you know that production having the highest weightage in the mechanical stream. All right. Now for that, here we are going to solve some common models which are continuously repeating models for the gate questions. I'm going to teach you. So now let us see the session. Right. Now have a look on this problem, all of you guys. Right. Now it's a casting method. So most of the times casting, you may ask that calculate the pouring time calculations, solidification time calculations, and also riser design my questions. Okay. Now sometimes they may also ask that the aspiration effect problem. Okay. Now here 1 2 marks question, which is previous gate question. Have a look on that. A rectangular block of steel cast iron 100 by 150 mm and 250 by 250 mm height is to be cast without any riser. Okay, without any riser. The block of molded entirely in drag in green sand flask is top gated. The cope of the flask is 200 mm height and the height of the molten metal during pouring is 100 mm above the cope level. A taper screw is employed and the gating ratio is given this much. Assume no energy losses in the system, right? Now time taken in seconds to fill the cavity if the taper screw with the cross section area of 500 mm square. So exit area is used. So here we have to calculate that time required for filling the mold cavity. So for these kind of questions, then immediately you are supposed to write the given data so that you will be able to find what are the terms or escaping from your you need to find. Okay, now first what is the casting volume? So now casting volume, we say that we see that is equal to it is 100 by 150 by 250 mm. Okay, now if you do that, then you're going to get it is 375 no 0000 cube you will get. So what is given? The block entirely in green sand flask and the height of the flask is given. Now for this you just construct a small diagram so that see, this is mold casting, two mold boxes. What they said in the problem, the casting is entirely kept in a drag. So as we know that it is a cope and it is a drag. Okay, now the volume is completely in drag box only and it is completely in drag box only, top gated. So now top gated means it is a top gate, right? Now the cope of the flask is 200 mm height from the during pouring. So now the cope height is given, that is 200 mm, right? Now during pouring the molten metal, see here the molten metal pouring into this. Okay, now this height will be 100 mm, this set, right? Now no energy losses, gating ratio is given. So now gating ratio is equal to it is 1 is to 4 is to 2, such that it is a screw cross section area and it is a runner area and it is a gate area. Okay, right, this is a given data and what they gave as is given. So screw cross section area is given, that is how much it is, 500 mm square. Okay, now for that we have to calculate how much time this cavity will take to fill. So how much time this cavity will take to fill with a molten metal. So this is you have to calculate. Now let us that filling time, calculate the filling time. Now filling time, we have a formula that you know filling time, or we can also call it as pouring time. Both are same, filling time or pouring time. So that is equal to, say, filling time TF, that is volume of casting is divided by, volume flow rate, volume flow rate, right? So now here volume of casting VC and volume flow rate is equal to, it is a choke area into velocity of the molten metal in the gating system. Okay, now how to calculate velocity of the molten metal in the gating system? So in this, what is the velocity of the molten metal? V we have to find. Now while you are calculating V velocity, V max is equal to, it is, under root 2g ht. Okay, now where ht is, see guys, so while you are calculating the velocity from where molten metal is pouring, so that height you have to consider. So now here total height is 300. So this 300 you have to consider as a total height. That means where molten metal is pouring from the mold cavity, that height you have to consider. All right guys, right? Now here, for that, so 2 into, it is G. You have to be very careful guys, because based on all dimensions are in mm, in that case you have to consider D is 9810 under root into ht is 300, so that you are going to get, it is 2426 mm per second will come. Now while you are deciding that, while you are deciding that VC, while you're deciding the VC, then, sorry, AC. So AC means it is a minimum of screw area and runner area and in-gate area. That means in which is a minimum value, that you have to consider. For that we have a ratio, na gating ratio. Gating ratio is given, it is 1 is to 4 is to 2. So now here screw area is 1 proportion and runner area is 4 proportions and gate area is 2 proportions. As we come to know by this ratio, S is a minimum, so that your AC value, choke area, this AC we call it as choke area. Now your choke area is become as AS is AS is given as 500 mm square. All right guys, now here we'll come to know that what is that pouring time. So we'll go for the next slide. Pouring time is equal to, it is, volume of casting is divided by choke area into V max. Right, now here it is a 3750000 is divided by, choke area is, 500 mm square, because it is the smallest one among the all gating elements, and it is 2426 mm per second. Now if you solve this equation, so that you are going to get, it is 0.39 seconds will come. So now your filling time is, for this cavity is TF, you are supposed to be, it is, 0.39 seconds. All right guys, now here you have to be very careful while you are taking the Z, as well as while you are calculating the T also. Now so from where the molten metal is pouring, so from there you have to calculate the T. So here the molten metal pouring from here. Okay, so that is the reason why. So here I'll write the diagram again. See, it is we consider it as the mold box entirely in track box. Okay, now this volume we have already calculated. This is a cavity, right? Now it is top gated this side. So now it is top gated. So where the molten metal is pouring, so it is pouring from certain height, 100 mm from the cope level. So this is 100 mm from the cope level. Now cope height is given in the problem now, right guys? Cope height is given in the problem, that is 200. Now your total ht is equal to, it is 100 plus 200, so that you are going to get it is a 300 mm. So like that. Okay, now you are calculating ac. While you are calculating ac choke area, we have to select which one is a minimum among all gating elements, that you have to select. So among all these, by this proportion, grating ratio proportion, we'll come to know that smallest proportion is the sprue area. That is why we are seeking sprue area is a final area. Then based on that, you have to calculate c. Right, now here I'm taking this area, choke area, into v max, so that I'll get 0.39 seconds. Hope you understand this. This is a gate 2 mass question, guys. All right. Right, next question. Right, a down sprue length 180 mm has a diameter of 20 mm at the top end. The liquid molten metal in the pouring cup is maintained 60 mm height. What should be the theoretical diameter of down sprue, its lower end, to ensure that there is no aspiration effect? Okay, so now it is also a previous gate question. It is also previous gate question. Okay, for 2 marks. Okay, guys, you understand previous question? Please do respond. Right, right. Okay, down sprue is 180 mm. Now with the help of a small diagram, I'm just explaining this. Okay, now here I just used to draw a small diagram of sprue. It's a sprue, down end of the sprue and top end of the sprue. And as we know that it is a pouring basin, and it is a sprue. All right, guys. Now in the problem what they gave, so a down sprue length, so sprue length is given, that is 180 mm. Okay, right. Now what is this diameter of the top end of the diameter? So if I take section 1, it is section 2, and it is section 3. So from there, here d2 is given how much, guys? It is 20 mm is given. Okay, so as a diameter of 20 mm at top end. The liquid molten metal in the pouring basin is 60 mm height. So now here the liquid molten metal in the pouring basin, its height is 60 mm. Okay, now this is heighted. Now here I'll write it is height of the pouring cup. HC is the height of the pouring cup is 60 mm. Now height of the sprue is 180 mm. Now so total height is equal to, it is HC plus HT, such that HC is 60 plus this fellow is 180, so that you are going to get it is a 240 mm is a total height. Clear, guys? Understood? Now what we have to find, so at the d3 end, what is the diameter we have to find to avoid aspiration effect? Okay, so as we know that one relation to avoid the aspiration effect, so that is now let me write that. To avoid aspiration effect, to avoid aspiration effect, so we have a relation that we have derived now, right? So we have a relation that is a3 is divided by a2 is equal to, it is a hc by ht under root. So now where a3 is a area of the cross section at the down. Okay, now a2 is the area of the cross section at the top end of the sprue. Okay, now if you want I can write. So now here a3 is a cross section, a3 is a cross section at down sprue, down end of sprue, down end of sprue. All right, now a2 is a cross section at the top end of sprue. All right, guys. Okay. Now, as we know that HC and HT we know na, so that is A3 by A2 is equal to HC. How much HC? HC is given 60 and HT is 240. HC is 60 is divided by 240 under root. Okay, right. Now we can write that A3 is pi by 3, sorry, pi by 4 d3 square is divided by pi by 4 d2 square is equal to, it is, if you solve that, then you will getting it is 0.5. Okay, now pi by 4 will get cancelled here na, so pi by 4 will get cancelled over here. Now you are going to get it is you know d3 square. Oh my god, 1 minute, 1 minute. Now it is gonna be a d3 square is divided by d2 square is equal to, it is 0.5. Yes, guys. Now from here we need to find d3 na. So now d3 equal to, I can write it is it is d2 into, it is under root 0.5. Now here d3 is equal to, d2 is how much given? D2 is given in the problem na, that is 20 mm. Okay, now 20 into, it is 0.5 under root. Now if you solve this, now you're going to get it is 2 3, it is 14.14 mm. Okay, so to avoid aspiration effect, to avoid aspiration effect, to avoid aspiration effect, down screw diameter is, down screw dia is 14.14 mm should be there. Okay, now here I will give you a small diagram. Okay, so now this will be the screw. To avoid this, what is this diameter? This diameter is 20 mm, and this diameter we have found that down screw diameter is 14.14 mm, so that you are going to get avoid the aspiration effect. Clear, everybody? Understood, guys? So please do respond. Yes, yes, yes. All right, right. Now let us go for another problem. Like this, you have to solve these kind of questions. Okay, you need to remember here very important one, this relation. Okay, so if you remember this relation, avoid aspiration effect, so that it is possible to you to solve this question very easy for 2 marks get. Okay, right. Next, see that in another welding question here, it is going to happen. Right, two metallic sheets, I just read the problem. Two metallic sheets, each of 2 mm thickness, are welded in a lap joint configuration by resistance spot welding. Okay, at welding, at welding current of 10 kilo amperes, the welding time of 10 milliseconds. So here what happened, 2 mm thickness of two sheets are welded in a lap joint configuration. Okay, so now I just drew that. Okay, so now this is a 2 mm thickness sheet, and this is also 2 mm thickness sheet. Okay, two sheets are in lap joint configuration, resistance spot welded. So a welding current is given, that is welding current is 10 kilo ampere, that is 10,000 amperes. Next, welding time of 10 milliseconds. So welding time t equal to 10 into 10 to the power of minus 3 seconds, so that you are going to get it is 0.01 seconds. All right, now a spherical fusion zone extending up to full thickness of each sheet. A spherical fusion zone extending up to full thickness of each sheet. That means the spot shape is spherical shape and it is extending up to full thickness of each sheet, so that my spot will be a spherical shape and is and is extending up to full thickness of each sheet, isn't it? So this is what the spot generated. Okay, now the properties of metallic sheet is given below. Okay, now the properties of sheet is given. So ambient temperature is given, and melting point temperature is given, density is given, and latent heat of fusion is given. Now specific heat is also given. Now contact resistance of the sheet is given, micro 100, that is 500 micro ohms. Now no conductive loss through the bulk sheet of material. To complete wall fusion zone melting temperature, the melting efficiency we have to find. So we have to find melting efficiency, okay, for forming this joint. Clear everybody? So first you write given data. So R is given, resistance is given, that is resistance is equal to, it is 500 micro ohms, such that 500 ohms, we just convert this into ohms, that is 10 to the power of minus 6 ohms. Clear everybody? Understood guys? Now here melting efficiency can be written as, heat required is divided by, that means heat required for melting this joint is divided by, heat generation. Heat generation, right? Now let us calculate that. So first we'll calculate heat generation and then we'll go for the heat requirement, right? Now heat generation Hg is equal to, it is I square RT. All right, now I is 10,000 amperes whole square into R is 500 into 10 to the power of minus 6 into 0.01 seconds, such that you are going to get, it is 500 joules will come. Okay, 500 joules will come. Now let's calculate that heat required for melting joint or forming the spot, or forming the spot. Heat required for forming spot. So that is equal to, how can we write? It is a mass of the spot into, it is a specific heat into, so we'll write a basic formula. From there you can derive that. That is what I said, that it is a sensible heat plus latent heat of melting. Okay, now here mass we can write, it is a volume of the nugget into density into sensible heat is Cp into delta T, means it is melting point temperature minus ambient temperature plus latent heat of melting, isn't it guys? Now here I just give you the diagram. Two sheets are lab joint configuration like this. Now here what is given? A spherical fusion zone extending up to full thickness of each sheet. Okay. Now a spherical fusion zone is formed, extending up to full thickness of each sheet. What is the thickness of the sheet is given? That is 2 mm is given, and this fellow is also 2 mm. So if these two are spot welded, so with the with the configuration of lap joint, and the formed nugget is spherical shape, and extending up to full thickness of each sheet. So that is the reason why here it is extending up to full thickness of each sheet. Now here it is a diameter of the spherical shape. So what is the diameter here? So diameter is going to be 4 mm. Now it is radius equal to, it is 2 mm. Okay, so diameter equal to 4 mm and radius equal to, it is 2 mm. Okay, now all this given na? So here how can we calculate the volume of this nugget? So it is a spherical shape. In the problem they mentioned it is a spherical fusion zone, that is a spherical shape. What is the formula for spherical? Now here I'll take here, this is equal to, so 4 by 3, so pi r is r is R is by 4 by 3 is R is 2 cube into 10 to the power of minus 9. So I'm converting my volume into meters. Why? Because density given in meters na. So that is why. What is the density given? It is 7,000 kg per meter cube. Okay, 7,000. And what is the specific heat? Specific heat is given, 800 joule per kg Kelvin. Okay, now here it is 800 joule per kg Kelvin. Now melting point temperature is 793, ambient temperature is 293. So melting point temperature is 793 and minus 293. Okay, and then, you know plus latent heat of melting. So latent heat of melting is how much is given? 300 kilojoule per kg. Now here 300 into 10 cube. So that heat requirement, if you solve that, you are going to get it is 352.5 joules will come. Clear, guys? So based on the data, so you just calculate heat required for formation of this nugget. I have calculated this much. So this much amount of the heat supplied, but only this much amount of the heat is required. Now melting efficiency is equal to melting efficiency is equal to, it is eta m is equal to heat required is divided by heat generation into 100. So now what is heat required? So it is heat required is 352.5 joules is divided by heat generation is 500 joules into 100. So that you're going to get it is a 70.5 melting efficiency. In this way you have to solve the problem. Clear, everybody? Understood, guys? Okay, so now melting efficiency we can calculate like this. Clear? Right. Now we'll just move for the next question. Now, in arc welding of butt joint, the welding speed is to be selected such that highest cooling rate is achieved. Melting efficiency and heat transfer efficiency are 0.5 and 0.7 respectively. The area of the weld cross section is 5 mm square and the unit melting energy required is 10 joule per mm cube. If the weld power is 2 kilowatts, so what will be the welding speed is close to in mm per second? This you have to calculate, guys. So it's another 2 marks question, right? What is the given data? Melting efficiency. So melting efficiency is equal to, it is a 0.5 and heat transfer efficiency eta t is equal to, it is 0.7. Okay, respectively. The area of the cross section of the weld bead. So now area of the cross section of the weld bead is 5 mm square. 5 mm square. Now unit energy required. So unit melting energy, that means for melting 1 unit you require, for melting 1 mm cube you require 10 joules. Okay, now the power is given for the welding, that is equal to, it is gonna be a how much? 2 kilowatt is given. Okay, now what we have to find? Welding speed we have to find. Okay, so that is in mm per second. So take care of the units, guys. Okay, now here see, I just draw the small diagram for you to understand this properly. Right, now this is what the well bead, right? Right, this is your cross section area of the well bead and power supply such that heat transfer. So means here you are supplying this much amount of the power, but because of the heat transfer efficiency, that means some losses to the surroundings. Now melting, actual melting efficiency is here this much. Okay, now what we have to find? Welding speed we have to find. Okay, so for that purpose we have a one relation, that, guys, what is that relation? That is, V into I into heat transfer efficiency into, melting efficiency is equal to, it is a area of the weld bead into velocity of the welding speed into unit melting energy. So if you remember these relation, so that it will be very easy to solve this question. All right, guys. All right. Right. Now let us go for substituting the values P. So Vi into P na. So it is P 2 kilowatts. Melting heat transfer efficiency given, melting efficiency given, area of the weld bead is given, and unit melting energy given. Only welding speed we have to find. Clear? Now let us go to that. So Vi. So here I'll write again. It is V into I into N into heat transfer efficiency into melting efficiency is equal to, it is area of the weld bead into welding speed into unit melting energy. Now power, how much power is given? 2 kilowatts now. V into I equal to power, that is 2 into 10 cube watts I'll write. So heat transfer efficiency, that is 0.7. Now melting efficiency 0.5. Area of the weld bead 5 square is given. Welding speed we don't know. Now melting efficiency is given 10 joule per cube. Now welding speed is equal to, it is I'll write it is properly, welding speed V is equal to, it is we can write it is 2 into 10 cube into 0.7 into 0.5 is divided by 5 into 10. So if you solve that, so that you are going to get, it is 14 per second will come. All right, guys. Clear? Sorry, 14 per minute will come. 14 per minute. Right. So if you want, you can check the units. So power units is watts. So watts I can write it is joule per second. So in what it is asking, per second only they are asking. So you will get per second only here. Now let's check. So it is above units are joule per second is a watt. Now here what is the area? Area is square into, it is into unit melting energy joule per cube. So now here what happened, joule will get cancelled. Okay, now joule will get cancelled and mm square will get cancelled. This will go up, so that is divided by second will come. So you can check the units like this also. Clear, everybody? Understood, guys? Please do respond. Okay, right. Now let's go for another question. That is see. So every every gate without sorry, there is no gate paper without metal cutting question. So here it is a metal cutting question. Okay, here let's solve this for 4 marks. For calculating the shear plane angle, 2 marks it says, and here for calculating the minimum power requirement is also for 2 marks. Sometimes you may get some linked answer question for 4 marks. Sometimes you may get 1 2 marks question, right? Now in an orthogonal, let us see that problem. In an orthogonal cutting experiment, HSS tool have been following tool signature in orthogonal reference system. That means ORS system it is given. Okay, right. Now given width of cut is 3.6 mm, shear strength of the workpiece metal is 460 Newton per square. Depth of cut is 0.25 mm. Coefficient of friction between chip tool interface is 0.7. What we have to find? Shear plane angle in degrees and also minimum power requirement. So note it this point, minimum power requirement. So for minimum cutting energy criteria, you have to consider. Okay. So in ORS system, so what is given? It is 0 degrees inclination angle, rectangle, and side cutting edge angle, sorry, side relief angle, end relief angle, side cutting edge angle, approach or entering angle, and also nose radius. Now here your rake angle for this is, rectangle alpha equal to here 10 degrees from this system. Okay, if you are having this system idea, so that you will be able to do this properly. Clear everybody? Understood guys? Okay, right. Now let us width of cut. So now width of cut is equal to, it is w 3.6 mm. Okay, width of cut equal to width of workpiece, width of workpiece, that is equal to B. Okay, now W equal to B you have to consider. Okay, next shear strength of material. Now shear strength of material, shear strength of material is 400 Newton per mm square. All right. Now depth of cut, D is equal to, it is 0.25 mm. So now here we can take it as T1. Depth of cut equal to uncut chip thickness. Okay, it is uncut chip thickness, uncut chip thickness. All right. Now what is given? Coefficient of friction mu is given, that is equal to, it is 0.7. All right. Now what we have to find? Shear plane angle. But minimum energy criteria we have to consider. For minimum energy criteria, what is the condition? For minimum energy criteria, for minimum energy criteria, so equation is 25 plus beta minus alpha is equal to 90 degrees. Okay, now we know alpha, we don't know beta, we don't know phi. So now we know that one relation, that is equal to tan beta equal to mu, right? Now beta equal to, it is tan inverse mu, isn't it guys? Now here, so tan inverse mu is 0.7, such that you may get beta equal to, it is 35 degrees. You will get 35 degrees, you will get, you know that beta, you know alpha, so find shear plane angle. So find shear plane angle, that is equal to phi equal to, it is 90 plus alpha minus beta is divided by 2, such that 90 minus 90 plus 10 minus 35 degrees is divided by 2, so that phi is equal to, it is 32.5 degrees. That means phi means shear plane angle, shear plane angle phi is equal to 32.5 degrees guys. All right. Now what we have to find next? Power required for cutting operation. So if the cutting speed is given, cutting speed Vc is equal to, it is 150 meters per minute, cutting speed is given. So right, now what is the power formula? You write that power formula. So power P equal to, it is a cutting force into cutting velocity, cutting force into cutting velocity. But we don't know the cutting force, so we know cutting velocity. Now how to find out the cutting force? For that they gave you one small clue. For that they gave you one small clue. What is that? They gave that shear strength. From the shear strength you have to develop your cutting force. Okay, that is a tricky. Here you have to use merchant circle formula, merchant circle relation. Okay, now shear stress is equal to, shear stress is equal to, here what is that? Shear force is divided by shear area. Now I just give you a small diagram to understand this. Right, now for this guys, have a look on this. This is the shaded portion is your shear area. Now for finding shear area, so you require length of shear plane and also width of shear plane B. Okay, so ls into B, so that ls shear area of the shear, area of the shear is equal to, it is length of shear plane into width of shear plane, so that you are going to get this. Okay, now how to find out ls can be find out. So here take this triangle, as we know that this is a phi and this fellow is a t1. Okay, now ls equal to, here ls equal to, it is sine phi, that is t1 by sine phi. Okay, now you just substitute that. So shear stress we know now. What is that shear stress? 400, 400 or 460? It is 460. It is gonna be a 460 Newton per mm square, and Fs we don't know, and so Ls is T1 sine phi, and ALS into B now. Now it is T1 by sine phi into B, such that it is gonna be a Fs into sine phi is divided by T1 into B, right? Now it is 460. From there you find that Fs is equal to, it is 460 into T1. How much, guys? T1 is given is T1 is T1 is given 0.25, B is 3.6 mm. 0.25 and B is 3.6 mm is divided by, it is sine phi is 32.5 degree. Okay, now if you solve that, you are going to get shear force is equal to your 616 newtons you will get. All right, now only you got shear force, but you require cutting force, but we have a relation in merchant circle, so let us go for how to have, what is the relation in the merchant circle. See that. So Fc cutting force is divided by cos of beta minus alpha is equal to, here it is Fs is divided by cos of beta minus alpha plus phi you are going to get. Okay, now as we know that we know Fs and we know beta, alpha, phi, everything we know. Now find out that Fc. So Fc equal to, it is Fs into, so cos beta minus alpha is divided by cos beta minus alpha plus phi. Now Fs is 616 into cos of beta is 35 degrees minus alpha is 10 degrees is divided by cos of beta is 35 minus 10 degrees plus 32.5 degree, isn't it, guys? Okay, from there Fc you are going to get, it is it is 1039 newtons you will get. So this relation you need to get from merchant circle. Okay, now I just draw a small merchant circle here, that is, it is a tool. Now the cutting force is going to be acta like this, and the thrust force like this, right? Now from there, and the friction sorry, shear force will be in this direction. Now normal to the shear force, Fsn will be like this, and frictional force acting downward and normal to the friction force. Now resultant of all these forces will become like this. Now this angle is beta and this is 90, and this is 90 minus beta, and it is beta minus alpha, and it is phi, right? Now from there, at this point 0, A, B, C, and D. Now, so from OAC and some OBC, you will get this relation. Okay, so you will get this relation. Merchant circle we have derived already. So now you can use directly this one. Clear, everybody, guys? Now, once you get that, so let us go for power. So power P equal to, it is Fc into Vc. Now here Fc is how much got? 1039 newtons into Vc. Cutting velocity how much, guys? Cutting velocity is 150 meters per minute. 150 meters per minute. But here you need to get power in watts now. So Newton meter is a joule, and per second we have to require. So per second, for getting the joule per second, for getting joule per second, you require seconds. That is why here Newton into it is 150 is divided by 60, so that it is meters per second you will get, such that you are going to get power is 2597 watts you will get. So approximately it is 2.6 kilowatts a power. This is how you have to calculate question. Okay, now what is your see rectangle, sorry, shear plane angle is 32.5 degrees, and your power is 2.6 kilowatts. 2.6 kilowatts. Clear, everybody? Your answer is for this question A. For this question is D is your answer. Clear, guys? Understood? Please do respond. Yes, yes. Very good, very good. Thank you, thank you, thank you, guys. Okay, like that you have to solve. You have to get the command on merchant circle so that it will be easy to solve this kind of question. Now let us go for another question, which is commonly asked in Taylor's two life equation question. This is also most of the times is repeating. Okay, so Taylor's two life equation, right? That is what is Taylor's two life equation, guys. Okay, now it is vt power n equal to c sir, where v is a cutting velocity, t is a two life, n is a exponent of Taylor's two life equation, and c is a Taylor's constant, right? So now see the problem. In machining operation, doubling the cutting speed reduces the two life to 1 by 8th of its original value. Okay, in a one particular machining operation, if I double the cutting speed, then two life is going to be decreased to 1 by 8th of initial value. Then exponent n in two life equation is okay. Now here we have to find n, two life Taylor two life equation n. Okay, now in the two cases are going to be happen here. So in the first case, so v1 equal to, we consider it as v, and the corresponding two life equation two life is we consider t. Now in this what happened, doubling the speed. So now in the second case, cutting speed is going to be double. That means to the initial value it is double. Now in this second case, what happened, if the cutting speed is going to be double, then two life is going to be 1 by 8th of original value, isn't it? 1 by 8th of original value. Now we have to find n. I gave you that one direct relation, that n equal to, it is log of v2 by v1 is divided by log of t1 by t2. All right, now from there, so log v2 is how much, 2v by v, and is divided by log of t1 by t2. T1 is t and t2 is t by 8. So now v will get cancelled, tt will get cancelled, this 8 will come up. Now here n equal to, it is log 2 is divided by log 8. So if you solve this, you are going to get n value equal to, it is 1 by 3. So now this your answer C. So it is another gate question for 2 marks. Alright guys, understood? So like that you have to solve. So for that you need to remember this formula, okay, and how to calculate. Oh my god, 1 minute, 1 minute. So for that you need to calculate, or you need to mention this formula. Okay, finished now guys. Now let us move for another question. Right. A steel bar diameter is turned on at a speed of 0.25 mm per revolution with a depth of cut of 4 mm. The rotational speed of workpiece is 160 rpm. The material removal rate in mm cube per second. Mm cube per second you have to calculate. Okay, now write that what is the diameter of the workpiece. Right, given data, dia of workpiece is equal to, it is 200 mm. So now I'm taking it as D. Now feed rate, feed of turning. So for turning operation, feed F is equal to, it is given 0.25 mm per revolution. All right, now with a depth of cut, depth of cut is equal to D is equal to, it is 4 mm. Okay, now rotational speed of workpiece, rotational speed of workpiece. So that is rotational speed is equal to, it is 160 rpm. Okay, now what we have to find? Metal removal rate. Okay, now here we have to find metal removal rate. So it is also commonly asked question. Finished guys. So write the given data and then what is the metal removal rate formula. So now here I'll highlight that with a other ink so that you will be able to give it now metal removal rate MRR is equal to, it is a speed into feed into depth of cut, so that you are going to get it some metal removal rate. So it is mm cube per minute. Okay, now here feed we know, depth we know, but we don't know the cutting speed, where V is the speed, feed, depth of cut, feed, speed, depth of cut. Clear guys? Now let us calculate that V. So as we know that cutting speed is equal to, as we know that cutting speed VC is equal to, it is so pi d n by 1000. Okay, pi d n by 1000. So here we know that pi into d is how much given guys? D is 200 mm and into n is how much you're going to get? N 160 given now. Right, now if I divide this fellow with 1000, I'll get speed in meters per minute. I will get meters per minute. I'll get. Okay, so now I don't require meters per minute. So because metal removal rate ask in mm cube per second, that is why my speed I have to take it as per second. So that is why here I'm not dividing with a v 1000. Okay, so here I'll get it is units of no. So pi d n by mm you will get. So here it is minutes. So if I divide it by with the 60, so that I'll get what is, it is going to be per second you will get, per second you will get, isn't it? Okay, that is why I just divide these fellow per second, such that my cutting speed is 1675 point 51 per second you will get. Now my metal removal rate is equal to, it is V into F into D, such that V is 1675 into feed is how much guys? Feed is 0.25, feed is 0.25 and depth of cut is 4 mm. Now from there if you solve that, it is gonna be a 1675.5. Actually here 0.5 I have to submit. Now it is gonna be a mm cube per second will come. All right guys, okay, like that you have to calculate the metal removal rate. All right, now let us go for another problem we'll solve. Right, so a through hole diameter drilled in a steel plate of 20 mm thickness, drill spindle speed is 300 rpm. Okay, now thickness of the plate, you write that thickness of the plate is 20 mm and speed is 300 rpm and feed is 0.2 mm per revolution is given. Okay, so drill over travel of the tool is equal to 2 mm. Now producing hole removal will be metal removal rate. So time for hole. Okay, first we'll calculate that time for producing one hole, that is equal to, it is L by F dot N. Now L equal to length of the tool travel. Okay, now length of the tool travel is, it is a through hole dimension. Okay, through hole dimension, its diameter. Now it is a thickness. Now here compulsory approach is there na, so AP1 and over travel of the tool. So now here L equal to, it is AP1, that means compulsory approach plus thickness plus overrun. Now compulsory approach for through hole is 0.5D I gave you, plus thickness of the sheet is 20 mm, overrun is 2. Now here 0.5 into diameter is 10 plus 20 plus 2, such that it is gonna be a 27 mm is a tool travel. Okay, right. Now from there, time for hole, time per hole is equal to, it is gonna be a L by F dot N. Now L is a 27 mm, is divided by feed is how much given, 0.2, and speed is 300, such that you are going to get, it is 27 seconds will come. So it will come in minutes, just convert that into seconds. Okay, now metal removal rate, metal removal rate also they ask you to calculate, right? So time for producing one hole and also metal removal rate will be, right, metal removal rate mmq per minute will calculate. Now metal removal rate is equal to, during drilling, area into F into N. Now area is pi by 4 d square into F into N. Now it is gonna be a pi by 4 10 square into, it is feed is 0.2 into N is 300, so that you are going to get, it is approximately 4712.38, 4712.38 mm cube per minute you will get. Okay, so now in machining time calculations, so you may get metal removal rate and machining time calculation. Most of the times you will get this kind of questions, guys. All right, so now hope you enjoy the session, guys. Okay, all of you. And now I have covered that metal cutting and metal removal rate, metal machining time calculations, and also metal removal rate calculations. Okay, so and I have covered some welding common questions and casting common questions, machining and metal cutting. 4 chapters I have covered. Okay, so thank you all of you. Thank you very much for your patient listen. Okay, so thank you all of you.